Okay, so today we're going to be talking about probability with combinations. This can get tricky if you don't kind of understand the basics behind it. So I'm going to hopefully explain that right away here with a good example. Okay, suppose you are dealt 5 cards at random from a well-shuffled standard deck. Find the probability that all 5 cards are hearts. Okay, now if you just start that out thinking about um, each card at a time, all right, you would get this first method here where on the first card, there are 13 hearts out of 52 cards. Okay, you could reduce that to 1 and 4, but you'll see the point here in just a second why I don't want you to do that. Okay, well, after you get a heart, there are only 12 hearts left out of 51 cards. Okay, and then you keep going with this process. You've got 11 hearts left out of 50, 10 hearts out of 49, and then 9 hearts left out of 48. So that would be kind of the way that you would go about doing it beforehand, right? You could even simplify that 13 times 12 times 11 times 10 times 9 in the numerator over 52 times 51 times 50 times 49 times 48. Now, when you do that, and I already did kind of the math over off to the side here, you get 154,440 over 311,875,200. Okay, which if you evaluate that, you get a number in scientific notation, which is about 0.000495. Okay, it continues on. What I'm going to show you today is a little bit of a shorter method to doing that. There's nothing wrong with this method, but the problem is you get really big numbers really quickly, and sometimes your calculators can't even compute those if the problem's big enough. So if we use a combination with this, it actually makes the problem simpler. So think of just the hearts. Okay, obviously over here we had 13, 12, 11, 10, 9. Okay, but remember, it's a combination. Order doesn't matter. So we actually can eliminate a lot of this extra stuff by using a combination. So if we think about it, there are 13 hearts to choose from, and we want 5 in a combination so that order doesn't matter. So if you have 13C5, that ends up being 1,287. Okay, so much smaller number than what we had over here. If you think about what you're doing it out of, again, probability is what you want out of possible. Okay, so 52 cards, again, you're choosing 5. There you get 2,598,960. Again, much smaller than this 311 million number. Okay. Now these are not the same number, but they're equivalent fractions because when you evaluate this, you also get 0.000495, whatever. So this method is what we're going to be focusing on today, is using a combination to get the same answer. Okay. So let's look at this other problem here. Sorry about that. 5 cards are drawn at random from a well-shuffled standard deck. Okay, find the probability that exactly 2 are hearts. Okay, so now this is a little different, and this is why I think method 2 up there helps us out. We only want 2 hearts. Okay, so again, how many hearts are there to choose from? Well, you've got 13, and we want 2 of them. Okay. Again, in the denominator, you've got 52 cards to choose from, and we're choosing 5. But implying that we want exactly 2 hearts also means that we need 3 not hearts. Okay, so we need exactly 3 non-hearts. So of the 13 hearts, we need 2 of them. Well, of the 39 other cards, spades, diamonds, and clubs, we need 3 of them. And so this is where this combination is going to help us out right now, because that's all we have to do. We need 13, or sorry, we need 2 hearts out of 13. We need 3 hearts or 3 non-hearts out of 39, and that all is out of the 52 C5. So all we have to do there, 13 C2, 78 times 39 C3, 139 over 52, which I realize it's already up there above, so whatever. 78 times 9139, and then divide that by the 20. Yep, that number. 274. And again, with these, you're going to round to 3 decimal places when you actually do the probability part. Okay, so pretty easy to do once you understand the combinations and how that works. Okay, so let's look at a few more examples here. Okay, 4 marbles are drawn without replacement from a bag containing 4 whites, 3 greens, and 5 blacks. Find the probability of drawing 2 green marbles. Pay attention to the original problem, the setup. You're drawing 4 of them, okay? But we want exactly 2 greens. Okay, so that means that you have 3 greens to choose from, and you want 2 of them. But that also means you need 2 non-green ones. Well, how many non-green ones are there? The white and the black, there are 9. Okay, how many total marbles are there? There's 12, and we are drawing 4 of them. Okay, so that's how we would set this up. 3C2, 2 green marbles out of 3, 2 non-green marbles out of 9, all divided by 12C4, 4 marbles out of the 12. Okay, and you can actually do that all in one stroke if you use your parentheses right. So 3C2 times, let's double parentheses just in case. 3C2 times 9C2, close your parenthesis, divided by 12C4. If you do that all, 0.218. Okay, so almost a 22% chance. Okay, find the probability of drawing 2 white and 2 black. Okay, so they're very specific here. So you've got 4 white marbles and you need 2 of them. You've got 5 black marbles and you need 2 of them. And again, that's going to be out of the 12 total marbles where you're choosing 4. So again, with your calculator, you can do it all in one fell stroke. 4C2 times 5C2 divided by 12C4, 0.121. Okay. It makes sense to think about it. If the more specific you get, the less probability you're going to have. Okay, because this one's pretty open. It doesn't matter what these other 2 marbles are. That increases the probability. This one's pretty specific. You need 2 white and you need 2 black. Okay, so that's why it's a little bit less. All right, last one. 3 marbles are drawn without replacement from a bag containing 4 reds and 5 blues. Okay, find the probability. All right, of all red. Well, okay, again, you can try to do this on your own if you want to, very first, if you want to pause it, okay. Otherwise, I'll just walk you through it. So 3 marbles are being chosen. Okay, you've got 4 reds to choose from, so you need 4 to choose from. You're choosing 3 out of a grand total, you've got 9 marbles to choose from, and you are choosing 3, so 9C3. Okay, so again, that's just going to be 4C3 divided by 9C3, 0.048. Okay. All right, 1 blue, implying that you get 2 red. So you've got 4 reds to choose from. You need 2 of them. And then got 5 blues to choose from, and you need 1 of them. And again, that's out of the 9C3. I'm not going to calculate that. You can calculate that on your own. But the last one, at least 1 blue. Okay, now let's think about that for a second. There's 2 ways that you can go about doing this. You can, you can calculate getting 1 blue plus 2 blue plus getting all 3 blue and adding those probabilities together. Or what's the only alternative? Getting 0 blue. Okay, these are the 4 scenarios that have to happen, right? This is the only one that doesn't fit the criteria. So again, think back to what we talked about in the very basic probability section about mutually exclusive events. That's the word I was looking for there. Mutually exclusive events. Either this has to happen or this has to happen. Well, this is what we want. All of this has to add up to a probability of 1. So to figure out this, 1 minus the probability of getting 0 blue, which would be all red, which we actually already figured. So the probability of getting greater than or equal to 1 blue is equal to this. You can use a shortcut here. So 1 minus this probability that we already did would give us the probability of getting at least 1 blue, which is over 95%. Does that make sense? Hopefully that makes sense on that last one there. Hopefully I explained this process out. But yeah, so that is probability with combinations.